Welcome back. How are you, friends? Hope you are doing good and enjoying with the lectures and getting something out of the lectures. Okay. In the last session, we had seen CE with RE amplifier, which has a negative feedback, and we got to know that if you want stability, lose gain, and if you want gain, lose stability, and gain is inversely proportional to stability. Just to summarize that point, I'm just writing one more time, and I'll explain a little bit about the H parameter model related to exact model and simplified model qualitatively. Now, last class, if you take CE amplifier, before that, because it is rubbed, it is easy for the reference. What I do, we are in chapter 2. We are in BJT amplifiers. Now, if you ask me the topic, what we are seeing, small signal AC analysis, BJT, small signal AC analysis. This is the topic which you are looking for. I think it is almost done. Okay. Now, if you take CE amplifier, right? This is the input and this is the output, and this is your load VCC. This is only AC circuit, and power supply is also there. Now, for this, if you take simplified model, right, assuming that RC or effective load for your transistor is less than or equal to 4K, if the load is less than or equal to 4K, then we can go for simplified model. And we got voltage gain AV without any feedback is equal to minus HFE into the load RC divided by HI. And we know that your voltage gain is depending on H parameters, and H parameters are depending on temperature, time, and replacement, right? Therefore, it is not stable. This is not stable, but high, but not stable, but it is high, but value is high. Now, coming to CE with RE amplifier, therefore, if you ask me, this is nothing but open loop. Open loop means without any feedback. There is no feedback. Open loop amplifier. Now, if you take CE with RE amplifier, remember this is simply revision, but I want to explain one point. CE with RE amplifier, and this is nothing but your having negative feedback, closed loop amplifier. Closed loop with negative feedback. Okay. Now, if you see that, this is RE, this is the input VI, and output V0, RC, VCC, right? The difference between CE amplifier and CE with RE amplifier is the RE, this is what is providing negative feedback. This is what I told before, and this is what is providing negative feedback. Therefore, if you provide negative feedback, the gain will be stabilized. That is what we had seen. This is nothing but voltage gain, AV is equal to, then we solved using H parameter model, simplified H parameter model, and we calculated what is V naught by Vi. Actually, we calculated all AC parameters, voltage gain, current gain, input impedance and output impedance, and we are looking for only voltage gain. Therefore, AV is equal to minus HFE into RC divided by HIE plus 1 plus HFE into RE. This is what we got, right? Then that time we discussed if 1 plus HFE into RE, if this is very much greater than HIE, then we can neglect HIE, then it is left with 1 plus HFE into RE. Then if you take 1 plus HFE approximately equal to HFE, because if HFE is in the order of 50, then 1 plus 50 you can take it as approximately 50. Then HFE, 1 plus HFE will be almost cancelled, then it is left with only ratio of resistors. Therefore, your voltage gain, let me say AVF. F is indicating what? Voltage gain with feedback. This is simply AV without any feedback. Therefore, AVF is equal to minus RC divided by RE. Therefore, this is depending on ratio of resistors. Always stable. Therefore, this is stable. Remember, don't remember this formula. This is derived formula. We need to remember this formula because this is original formula. If this condition is true, then only this is valid. If this condition is not true, then we cannot use this formula. Very important. Okay. Then this is stable but low. This is stable but the value is low. This is what we had seen in the last class. Then overall, if you see the observation point is what? If you want gain, lose stability. If you want stability, lose gain. That is what. Therefore, overall, I can say, therefore, tell me what is your gain, AC gain, right? Your AC gain, when I say gain, by default, voltage gain. If I don't specify anything, by default, you can take it as voltage gain, right? Therefore, your AC gain is inversely proportional to stability. This is very important. Your gain is inversely proportional to stability. What does it mean? If you want stability, then gain will be less. If stability is less, your gain will be more. Okay? I think you can just take it like a reference, which I already explained before, but this is what is important. Maybe you can write this black box. I'll give 1 minute time to write. Then after that, I'll explain something related to BJT using qualitative analysis. Okay. But what type of feedback and all, that part I will discuss for feedback amplifiers, because we have separate topic called feedback amplifiers, and in that we will understand in detail what is this feedback and how it is improving stability. All those things we can see from feedback perspective, independent of the circuit configuration. Okay, till now maybe whatever configurations we had seen: common emitter amplifier, common base amplifier, common collector amplifier, and CE with RE amplifier, right? For all these configurations, or whatever configuration you want to see later, let us say we are using H parameter model, whether it is exact model or simplified model, then we are trying to solve the circuits, and then we are trying to get the formula, or we are substituting the values in the formula, and then we are getting the answers. That is fine. Now my query is, we don't know, let us say we don't know anything about transistor operation, because we didn't see that part will be covered under device operation, that is fine, EDC. But now what I am saying, till now, even though did I take anything related to the device operation? No. We just took the BJT as a black box, and we took network analysis help, which is two-port network analysis. Then we defined the black box with H parameter model. Then we used that H parameter model to get all AC parameters: voltage gain, current gain, input impedance and output impedance, right? Now let me try to correlate the H parameter model, whatever we got from network analysis, right? Let me try to correlate, can we get that from BJT operation? I will not explain complete operation, but little bit I can explain. Therefore, we can correlate the mathematical H parameter model to the qualitative understanding of the transistor. Therefore, we will understand the significance of HIE, HFE, HRE, HOE. Till now somebody is giving us the values of H parameter, but now let's understand the significance of each H parameter, which is what is represented from two-port network analysis. Or what I say, maybe to make it interesting, let me say you forget whatever we had done till now. You don't know anything about H parameter model. You don't know anything about H parameter model, right? Now let's try to get the equivalent circuit, right, for your BJT using qualitative analysis. We don't know anything about two-port network analysis and all. For the time being, we just forget. Then let's see, can we get the equivalent circuit or not? Okay, that is what is the that is what I call it as qualitative analysis, without using mathematical equations, right? We can get the equivalent circuit also from the operation. Okay, let's see. Let me erase this part. Okay, now just don't write, listen, this is little bit related to concept. Now if you take BJT cross-sectional view, this is emitter, base, collector. Let me take NPN transistor, N, P minus. Emitter is heavily doped, base is lightly doped, and collector is having typical doping. I told everything is having its own significance. We cannot take emitter simply typical doping. If you take it, you will not get maximum current gain. Okay, that is what we are trying to see, the transistor action. Okay, let's see. Now I am speaking about active region. When I speak about active region, what is active region? Your emitter junction should be in forward bias. Therefore, this is connector like this. Let us say this is VBE. Okay, and this is in reverse bias. Therefore, we are applying VCB. Okay. Now, for your understanding, this is nothing but your active region. For your understanding, let us say the VCB is not connected. Now, when you apply VBE and what is the current, then let us don't apply VBE, then let's apply only VCB, let's see the current, then we will get it. That is very simple. Okay. Now, for example, if VCB is not there, case 1, only VBE is applied. Only VBE is applied. This is not superposition. When I say superposition, what is superposition? We have to inactivate, means we have to short it. I am not saying that we have to short it, open it completely. Therefore, this is not superposition. I am just applying in a different way. Only VB is applied. If only VB is applied, collector is left unconnected. Now this is emitter, this is base, and this is N plus P minus N. Now, but remember, in detailed operation of this device, you'll get it from EDC subject. Okay. Now, this is what is VBE. Now, we know that this is nothing but a PN junction diode, right? Then P is connected to positive, N is connected to negative. Therefore, you will see the current, right? Therefore, we will see definitely the current, but instead of explaining through current, let me explain through electron flow. Therefore, let us say 100 electrons are entering into PN junction diode. Therefore, you will get loop current because this is forward bias PN junction diode. When I say forward bias PN junction diode, there is a current, significant current due to majority carrier. The majority carriers of emitter electron, the majority carriers of base holes. Therefore, whatever maybe you will see the current due to majority carriers of your PN junction. Therefore, you see the current. Let us say 100 electrons are entering into emitter. Let us say 100 electrons are entering into emitter. When 100 electrons are entering into emitter, then those electrons, because what are the majority carriers? The majority carriers are electrons. There are so many majority carriers because it is heavily doped. And let us say your base is having, with respect to your emitter, you know how many electrons are there? You remember I told, right? The typical doping concentration is nothing but what? 10 to the power of 16 or 10 to the power of 14 per centimeter cube. What does it mean? Per centimeter cubic structure of your semiconductor after doping, right? 10 to the power of 14 electrons are there. What does it mean? 1 crore electrons. But when I am representing here, I can say hardly 70 or 80 dots. But strictly speaking, 1 crores electrons are there per centimeter cube. Okay. But for your understanding, you can say 1 dot is group of electrons. You can imagine in that way, then it will satisfy. Okay. 1 dot, even I am saying an electron, 1 dot is nothing but millions of electrons. Okay. Such millions of electrons, if you combine, you will get billions of electrons. Okay. Then base, it is also having majority of holes, but it is not one hole. You imagine that millions of holes, but each hole is representing group of holes. Okay. Now, and then your collector is typically doping, but I am not bothering about collector because nothing is connected. That is fine. Now let's see, if 100 electrons are entering into emitter, then when electrons are entering, there are so many electrons, they will move successively. That is what is called drift component, and they will enter into emitter. Then they are entering into base, and there is no way they have to come out of the base. Then they will reach the emitter terminal. Okay. Therefore, once the electrons which are entering into base, and there is no way they have to come out of the base and then reach the other terminal of the battery. Therefore, what you get? Definitely you will get here 100 electrons. This is what your forward bias current. Therefore, if you ask me emitter current, your emitter current IE is forward bias current. Emitter current IE is forward bias current, and this will be in the order of, let us say, milliampere. Okay, done. Don't write. Now case 2. What is case 2? Only VCB is applied. Only VCB is applied. When you say only VCB is applied, now the same structure, this is emitter, this is base, this is collector, N plus P minus N. Now when you apply reverse bias voltage, because your collector junction should be in reverse bias, then only you will get active region. Okay, therefore basically you can say this is what is providing you active region. Therefore, because we want active region, this is what is giving you because we are looking for amplifier. When I say amplifier, the BJT should be in active region. Okay, now here again same, we have two holes and typical number of electrons because typically doped. Okay, this is fine. Remember, I am not going to again the PN junction diode operation. What are all the current components which are present inside the PN junction diode? That part again I am not going to the details. I am just taking like this is in forward bias because this is nothing but your emitter junction. When you say this is what your emitter junction, this is your emitter junction, this is emitter junction, and now this is collector junction, this is collector junction, right? Therefore now we are bothering about collector junction, right? Then this is reverse bias. Then whatever current you get, let us say collector current, whatever collector current you get, this is nothing but what? Reverse bias current. That is due to, because PN junction diode is under reverse bias. When PN junction diode is under reverse bias, we get current due to minority carriers, not due to majority carriers. Okay, then that current will be in the order of microampere. If you treat the forward bias current in the order of milliampere, then you can say your reverse bias current will be in the order of microampere. What does that mean? What does it mean? The current can be neglected. You can say because the current through PN junction diode, reverse bias PN junction diode, you can take it as approximately 0. The current through forward bias PN junction diode, that you can take it maximum. Okay. Therefore, now we have two junctions, emitter junction and collector junction, right? Out of these two junctions, maybe just to differentiate only emitter junction and the collector junction, right? Then we have only two junctions. Then emitter junction is in forward bias and collector junction is in reverse bias. If that is what is the scenario and emitter current is milliampere of current, collector current is microampere of current. Expected. This is what is expected. Forward bias PN junction diode, maximum current. Reverse bias PN junction diode, minimum current. Let's combine. What is active region? Forward bias PN junction and the reverse bias PN junction. Let's combine. This is what is the combination, right? Now take it. Instead of drawing again one more and then applying both, already I have drawn this, let me explain from here only. Okay, just take these two, then I'll explain case 3, third point, but don't disturb the original cross-sectional view connection. You have to draw again, once again, the third one, both VBE and then VCB are applied. Okay, before that you write these two. Okay, I'm not explaining why forward bias current is in the order of milliampere and why reverse bias current is in the order of microampere, but typically we know that forward bias PN junction diode carries current in the order of milliampere and reverse bias PN junction diode carries in the order of microampere, because forward bias current is due to majority carriers and reverse bias current is due to minority carriers. Okay, take it. Just one point, because I represent with 100 units of electrons. Remember, it's not 100 electrons, 100 units of electrons. Each unit, like a dot, is representing group of electrons. Okay, therefore 100 units of electrons, 100 units of electrons. If I give some number here, maybe I can say this is what is our electron flow. This is current flow, but this is what is electron flow, right? Therefore, let us say maybe you can imagine that some 0.1 electron. Don't think that where we have 0.1 electron. We don't have 0.1 electron, right? But I'm just saying it is 0.1 electron because 0.1 is nothing but, let us say the 0.1 unit. 1 unit is 1 million. Then 0.1 million. Therefore, that is integer number. Therefore, this is what is 0.1 electron. How many are entering? Therefore, same number of electrons are coming out. 0.1 electron. And people call this current as, whatever current which we have, right? People call this current as IC is equal to ICBO. What is ICBO? Collector to base reverse bias current when emitter is opened. Therefore, collector to base reverse bias current when emitter is opened. That is what? Or the collector current reverse saturation current. Because if you take PN junction diode, the reverse saturation current is nothing but I0, right? I0, kind of open circuit and the current. That is what is I0. Here, this is also reverse bias PN junction diode current, but through collector. Therefore, IC not. That is the representation people followed. You can take. Even though I'm adding few points in between, just listen while I'm speaking. Until I say that, you can write. Okay? I'll wait for 1 more minute. Try to complete in 1 minute. Then I'll continue for third one. Over? Okay. Now, you have to draw once again. But I'm going to use the existing one. This is what is point number 3. What is point number 3? Both VBE and VCB are applied. Okay. When both VBE and then VCB are applied, we know that there is a current, right? Just listen. This is what is very important, right? Therefore, tell me what is our emitter current we are expecting. Emitter current I am expecting in the order of milliampere, which is forward bias current. And what are you expecting the collector current? I am expecting collector current, which is reverse bias current, in the order of microampere. That is what is my expectation. But you know, once you combine both VBE and then VCB, you will get unexpected output or unexpected action. That is what people call it as transistor action. Okay, that is what, due to which we are getting amplification. Okay, let's see. Now, let us say the same thing. 100 electrons are entering into emitter. When 100 electrons are entering into emitter, then we know that your emitter is heavily doped. Same, for emitter is heavily doped, there are so many electrons. Each dot is representing group of electrons. And let us say each hole is representing group of holes, and this is typically doped. Remember, I'm explaining qualitative part. The mathematical part you will get it from device operation, okay? EDC. Now, if you take that, if 100 electrons are entering into emitter, just listen, this is what is very important, right? Then, when 100 electrons are entering into emitter, they are moving through drift component, now entering into base. When they are entering into base, now it has two options, either come out of the base or enter into collector and then move through collector and then come out of the collector. It has two paths. What I mean is, let us say there is a battery having only one branch, or whatever maybe we have two branches. Then that is nothing but what? Whatever current you are getting I, that I will be equal to, let us say, I1 and then I2. Right? This current is equal to this current plus this current. Right? Therefore, now if you ask me 100 electrons which are entering into emitter, I am just taking examples. Don't take these values as granted. That is for your understanding purpose. Okay? Because I am not explaining all the things at the same time. If I try to explain all the things at the same time, we will not understand. Everything will be incremental. Okay? Therefore, 100 electrons are entering into emitter, then moving through emitter, entering into base. Now, which is easier path? Entering into collector and coming out of collector, or coming out of base? Actually, entering into collector, that is what is more feasible for the electrons which are entering into base from emitter, because when they are entering into emitter, there is something called diffusion current. Therefore, when the diffusion current is present, then only little bit distance, that is the reason why the base width is very small. Therefore, when they enter into base, then only small distance they will travel. While traveling from emitter to collector, because we have few vacant states which are nothing but holes, only few electrons will come out of the base. Almost all electrons which are entering into collector, they will be coming out of collector. Then let us say, again example, let us say 2 electrons are coming out of base and the remaining almost 98 electrons are coming out of collector. This is transistor action. What are we expecting through collector? We are expecting through collector is almost zero current, right? But we are getting collector current almost equal to emitter current. That is because of what? That is because of transistor action. To get this transistor action, the size of the base is very small. Let us say the size of the base is not very small. If base size is more, then it will see more number of holes. Then the electrons that are entering into base, they will come out of the base. More number of electrons will come out of base. Only remaining electrons will enter into collector. Therefore, instead of 98, maybe 90 and then 10. Therefore, then in that case, your collector current is not equal to emitter current. Remember, I want collector current is equal to emitter current. If to get collector current is approximately equal to emitter current, right? Then what is the size of the base, and then what is the size, base doping concentration, etc. Now, in this scenario, right? What is your IC now? Can I say your IC is approximately equal to IE? If IC is approximately equal to IE, then people call this as, you can say, some factor called alpha. Therefore, here this is what people call it as alpha. Therefore, IC is equal to alpha into IE. When I say IC is equal to alpha into IE, where alpha, in this example, can anyone tell what is alpha? Yes, 0.98. Therefore, what is alpha? Alpha is 0.98, means 98% of your emitter current is nothing but your collector current. 98% of your emitter current is nothing but your collector current. Therefore, IC is equal to alpha into IE. In this example, therefore, let me call this as equation 1. Therefore, that IC, 98 electrons, whatever I told, due to what? Due to transistor action. Therefore, this is due to transistor action. What I do, let me erase this. I can write due to transistor action. Due to transistor action. What is transistor action? The collector current is expected to be almost 0, but we are getting almost equal to emitter current, which is unexpected from reverse bias PN junction diode. Actually, this is reverse bias PN junction, right? but we are getting reverse bias PN junction diode current is almost equal to forward bias PN junction diode current, which is unexpected. That is what is called transistor action. Transistor action means, why the name transistor? Okay, that part I will come to you. Let me complete this part. Therefore, tell me, due to transistor action, what is your IC? Your IC is approximately equal to IE, not absolutely equal to IE, but approximately equal to IE. Then there is a mathematical parameter which is nothing but alpha. IC is equal to alpha into IE. You can call this as equation 1. Therefore, whatever collector current you are getting, that is due to emitter current, that is nothing but IC is equal to alpha into IE. But remember, we have another current that is due to reverse bias. Therefore, what is that current? I am not showing that. That current is not represented here. This current is only due to emitter current. That's why that is what is called due to transistor action. Now, if you take reverse bias PN junction diode current, that is due to minority carriers, that current is nothing but ICBO. Let me call this as, or you can say, due to collector junction reverse bias. Then what is your IC? Your IC is equal to ICBO or IC0. This is equation 2. Therefore, IC due to transistor action is alpha into IE. IC due to reverse bias PN junction diode ICBO. Strictly speaking, you can neglect ICBO because this current is in the order of milliampere, which is forward bias current. But I am not neglecting it. Maybe when you solve the problems, we can neglect ICBO. But I want to give you the exact equation such that will be used for DC analysis. Actually, I am explaining all these things for DC analysis. What it may be. Therefore, what is your total current? Therefore, now the total collector current IC is equal to alpha into IE, that is due to transistor action, plus ICBO, that is due to reverse bias PN junction diode. Therefore, this is what is our IC in terms of IE. Right? Therefore, what is your IC in terms of IE and then its own reverse bias current. That is what is straightforward. Right? You can call this as equation 3. Okay? Whatever I am explaining here, right? Therefore, now tell me, and we know that KCL. What is KCL? If you write KCL, can I say your emitter current is equal to base current plus collector current? That is due to transistor action. Right? Therefore, what is your emitter current? The emitter current is equal to base current plus collector current. KCL. Therefore, your emitter current IE is equal to IC plus IB. Right? Now, if you take due to transistor action, right? And one more thing, this is what is, you can call this as equation 4. This is what your KCL. Now, we know the relation between IE to IC due to transistor action. Okay. Now, I want to know the relation between IB to IC due to transistor action. Therefore, now tell me, can I write 98 is approximately equal to something into 2? Can I write like this? That 98 is equal to something into 2 because I want to write in terms of base current. Therefore, what is that? This is what people called it as beta. In this example, the beta is nothing but 49. Right? Therefore, what is 49? 49 into 2 is 98. Therefore, beta is 49. Right? Therefore, IC in terms of base current, IC is equal to beta into IB due to transistor action. And what is IC? IC is equal to alpha into IE due to transistor action. Therefore, due to transistor action, IC is equal to alpha into IE, and then due to transistor action, what is IC? IC is equal to beta into IB. Right? Therefore, I can write here, or I can write here. Therefore, due to transistor action, what is your IC? IC is equal to beta into IB. Okay. Now I want to get the relation between alpha and beta. Okay. If I want to get the relation between alpha and beta, right? Therefore, can I write it? Which is not, can I divide it by? Therefore, 4 implies if I divide it by IE by IC, then IC by IC 1, then IB by IC. What is IE by IC? IE by IC is nothing but 1 by alpha 1 plus, what is IB by IC? IB by IC 1 by beta. Therefore Therefore, 1 by alpha is equal to 1 plus beta by beta. Then what is your alpha? Alpha is equal to beta divided by 1 plus beta. This is what is the relation between alpha and beta due to transistor action. And at the same time, and similarly, what is 1 by beta? 1 by beta is equal to 1 by alpha minus 1. Then this is simply alpha and 1 minus alpha. This is what is your 1 by beta. Then what is your beta? Then beta is equal to alpha divided by 1 minus alpha. Therefore, we got to know the relation between alpha and beta. Alpha in terms of beta, alpha is equal to beta by 1 plus beta. And what is beta? Beta is equal to alpha divided by 1 minus alpha. Okay? That is what? Due to transistor action. Right? Therefore, now if you see, but now I want to get complete equation. Similarly, it is similar to what? The total collector current, right? Which is nothing but due to transistor action, whatever current we got, alpha into IE plus ICBO. That is what we got. Similarly, this is due to transistor action, IC is equal to beta into IB, right? Then I want to get total current including reverse saturation current also. Then I can use equation 3. Therefore, you can write total collector current equation. Total IC in terms of IB and ICBO. Then IC is equal to, we know that IC is equal to alpha into IE plus ICBO. Right? Then what is IE? We know IE from KCL. IC plus IB. For IC plus IB plus ICBO. Right? Then can I take IC common here? If I take IC common, 1 minus alpha. Because this alpha IC, if you take it to left hand side, then you will get alpha into IB plus ICBO. Then what is IC? IC is equal to alpha divided by 1 minus alpha into IB plus 1 divided by 1 minus alpha into ICBO. What is alpha by 1 minus alpha? Alpha by 1 minus alpha is beta. Therefore, IC is equal to beta into IB plus what is 1 by 1 minus alpha? 1 by 1 minus alpha. Maybe if you calculate, what you get? Actually alpha, what is 1 minus alpha? 1 minus alpha is equal to 1 minus, what is alpha? Beta by 1 plus beta. Then if you take it 1 plus beta by, then you will get 1 by 1 plus beta. Then 1 by 1 minus alpha is 1 plus beta. Therefore, it is 1 plus beta into ICBO. Remember, this is what is your total collector current in terms of IB as well as ICBO. Here, this is what your total collector current in terms of IE and then ICBO. Right? Now, this is what is our ultimate equation, right? IC in terms of IE and then IC in terms of IB. Actually, this is what we use for common base and this is what is for common collector. But if you neglect ICBO, then your IC is approximately equal to beta into IB. Okay? Then remaining things we'll see in the next session. Before that, you can write down all these things. Okay? Take all these things. See, if you take only transistor action, neglecting reverse saturation current, then your IC is equal to beta into IB and IC is equal to alpha into IE. But if you want to write in terms of complete equation without neglecting reverse saturation current also, then IC is equal alpha into IE plus ICBO, then IC is equal beta into IB plus 1 plus beta into ICBO. Okay. This is what is part 1. Part 1 in the sense, this is what is IC in terms of IE, and this is what is part 2, IC, writing IC in terms of IB. Actually, I need this equation. IC alpha into IE plus ICBO or this equation. The equations which are in box, those things only you can take them as granted. Okay. You have to draw again the cross sectional view of your BJT separately under point number 3. I will stop now. Okay, let's continue in the next session.